Hi, everybody. Uh, I'm very happy to be talking with you this afternoon about our project on tropical peatlands. Because there isn't much time, I can't cover everything in the project, so I'll just focus on something we've been working on recently and where we're going from here. So, as you may know, drained tropical peatlands in Southeast Asia release carbon dioxide, either by aerobic decomposition by microbes, or it could also happen by fire. And our project has been focused on trying to develop a basic understanding of how these systems work, and therefore to be able to use that information for mitigation, for decision support, for things like that. Okay, so the area around Singapore, as you may know, there is quite a bit of area of low-lying coastal regions that are covered by tropical peatlands. These are environments where the soil consists almost entirely of organic matter, by definition more than 90%, but usually more than 99%, because waterlogging in the swamp suppresses the decomposition of plant matter. So over 99% organic matter means also that it's over 99% combustible. So if you have a fire in a peatland, not only the plants catch on fire, but the soil can catch on fire, and it's almost impossible to extinguish until the water table rises. So the fires are a contributor to haze, which is an expensive problem. But even without fires, you still have substantial greenhouse gas emissions when peatlands are drained. It's about 20% of land use and land cover change anthropogenic emissions, or about 2% of total human emissions are from draining of tropical peat swamps. Maybe not much, but much more than Singapore, I suppose. First, let me just cover some basic things about the way that the peat accumulates in peatlands. So peat piles up. I'm going to try to press the right button here. There we go. Peat piles up in mounds. This is a section through a peat swamp in Sarawak, and these lines are actually the water table. So at first, it might seem very strange that the water table has a curved or mounded shape coinciding with the peat surface. Why doesn't the water just drain out of the peatland? Well, there's two things to notice. First, the scale is very exaggerated, so the curvature is actually very, very gentle in both the landscape and the water table. But also, the reason it does drain out, it's just continuously replaced by rain coming from the sky. So on some level, these landscapes, they have to have this kind of mounded or domed shape, because rain comes from the sky, it has to go somewhere, it goes downhill. And as you get closer to the streams or rivers or ditches bounding these peat mounds or peat domes, the amount of water that needs to be transported per perimeter is larger, so the gradient has to be bigger. So they have to form into these mounds. And one of the things that people figured out in the 1970s or 1980s in tropical, temperate peatlands rather, is that there's some maximally curved shape for these structures, because if they're too curved, then water flows out too fast. There's no more water logging, and peat doesn't accumulate. If they're too flat, then you get pooling of water, and peat accumulates faster, because it accumulates because of suppression of decomposition by water logging. Okay, so there's this sort of feedback cycle where you have accumulation of peat, which generates the shape of the landscape, the topography and its hydrologic properties, its transmissivity. That determines how groundwater flows, and that, along with rainfall, determines where the water table is, which in turn controls how peat accumulation occurs. So this is like a dynamical system. So in order to understand how this stuff works better, I established a couple of field sites in Brunei, on Borneo, in one of these peatland areas. And then we did a lot of different things. Again, I just want to sort of have one shock and awe slide to say the different things that we were working on, but I'm only going to focus on this last thing, peat formation and decomposition. But besides setting up the field sites, we also did a lot of work on the biogeochemistry of peatlands, on soil processes, soil efflux. Then there's a big engineering component of the project to build sensors led in recent years by Adali Ali from our group. But again, I'm going to focus on this. So I wanted to have a slide with everybody's name. It kind of looks like the ending credits to a Star Wars movie, but anyway, there are many people in SMART, many students, many interns, our counterparts in Brunei, and lots of collaborators. Okay. So just to focus on this one question for the duration of my time. And an interesting thing that you may have noticed about that earlier slide showing the water table is that the shape of the water table is always the same. So it moves up and down, but the shape of the water table remains static, even as the water table rises during rain and falls after rain. So this is these vertical bars, that's the rain. The water table shoots up, but this looks like one squiggly line, but it's actually 5 different places that we're measuring the water table relative to the surface that are separated by more than 2 kilometers. So it fluctuates in a very unusual way. Now, this is partly because the hydrologic properties of the peat are grossly similar in different parts of the peatland because it's formed by basically the same process. But that's not enough to explain the uniform fluctuation. It also has to do with the fact that the curvature is uniform in a particular kind of way, which I'll explain in a second. And so once the peatland has this sort of limiting curvature, you get this uniform fluctuation of the water table. Again, unfortunately, I don't have time to explain much, but it turns out that we can compute what that curvature has to be. By curvature, I mean the Laplacian of the peat surface elevation, or the sum of the second partial derivatives of the surface elevation in 2 perpendicular horizontal directions. And that has to be equal to the time average of the net precipitation divided by the time average of the transmissivity. And I would love to tell you more about how we compute that, but I can't do it now. So what this does, though, is it says that there's a particular pattern to how the peat landscape forms. It has a stable curvature at which the production of peat is balanced by decomposition, and it grows towards that shape. But because it's a curved shape, it's lower towards the boundaries where the rivers are, and so it reaches that state first, near the boundaries. So the interesting thing about that, maybe, is that it means that the peat near the surface can be very old near rivers because the peat surface stops growing first there. And the peat surface can be young further from the rivers because that's where it's still growing until it reaches its happy, stable, uniform Laplacian, uniform curvature shape. So that was something that we hadn't really predicted or anything, so we went to make a lot of measurements and write a model to simulate how the peatlands grow. So a lot of field work, and 20,000 lines of code later, we produced this figure. All of these little circles are radiocarbon dates, and the point of the figure is just to show that the simulation of the growth of the peat surface coincides nicely with what we measure with the radiocarbon dates, but also there's this qualitative thing, which is that the peat near the surface, closer to the river, is old. So that made us think that maybe that we were onto something. So something about this model is that it predicts a stable shape for the peat surface, which means that it defines a capacity of a particular drainage network to hold carbon given a particular pattern of rainfall. If the peat surface is too curved, then it will decompose. If it's not curved enough, then it will grow. And that means that we can predict the effects of changes in the rainfall pattern, but also drainage networks. So in natural peatlands, you have rivers that drain all of the water that comes out of the sky and flows out through the peatland. But when people convert peatlands to agricultural uses, usually oil palm or acacia, they make canals. And when they do that, they subdivide the landscape into a much finer grid than the landscape is naturally divided by rivers. So these, I don't know if you can see all of these little fine lines. This is the Barham River in Sarawak, and all of these little lines are drainage canals inside oil palm plantation. So just to give you an idea of the scale, this is about the size of one of the peat domes at our field site. So it's about 5.4 kilometers on a side. This is the grid just for scale in a typical oil palm plantation. So note the different scale. This is how it's divided up into small pieces. As the stable shape of the peatland, it's a solution to Poisson's equation, something where the Laplacian of the surface elevation is uniform. So we can compute, and here the color is just the height. So if you start out with a square that is curved like this, and you cut it in half, but you keep the same curvature, it just can't hold as much carbon if you cut a canal here. Same curvature, different amount of carbon. So that means all of the carbon that was there has to go somewhere. It will either decompose, releasing greenhouse gases, or it will burn. So this very simple model gives us a way of predicting fire risk and greenhouse gas emissions in the long term, although we can also compute the shorter term emissions dynamically. Okay, so, and this is just something to try to convince you that we can compute what we say we can compute. As you divide a region into smaller areas, the storage capacity goes down. If you divide it into long, thin pieces, it has a lower storage capacity, which maybe makes sense. Okay, so what we're working on now is to try to use these basic findings to try to develop tools. So first we need to define drainage networks, so we're working with some remote sensing people to try to use, for example, radar data to better spot where the rivers are, so that we can define the boundary conditions, the starting boundary conditions, and then compute what will happen to the landscape after different management interventions. So again, to summarize, through our project, we've been trying to understand how peatlands work. There's this basic, or very basic finding about the geomorphology of peatlands has, turns out, management implications, and we're now working to try to use that to build decision support tools for people developing plantations, people in government managing peatlands, that sort of thing. Finally, just to thank my team, I tried to pick the most embarrassing pictures that I could find. And I'll welcome any or one or two questions. Thank you.
Thank you, Dr. Cobb, and thank you for keeping on time as well. Much appreciated. Ooh. I'll stay away from the speaker. Does anyone have a question or two, Chan?
Yes, perfect. I'm just curious, did you measure the water table
In 2015? Yes.
So how different that compared to 2012?
Lower. It was a dry year. In Northwest Borneo, the timing of the dry period, if I remember right, that was the year when it was dry, oddly dry in January and February in Northwest Borneo, which is very unusual. Usually those are the wettest months of the year. So the early part of the year was dry, and then it re-wetted. But still, this is a pristine peat swamp, so the lowest excursion of the water table is still only like 30 or 40 centimeters below the surface. I don't know whether I answered your question. Oh, yeah, I can talk with you more about that, actually.